Hey there. So it has been a while since I have posted an update on the 6009 Playground Homebrew Computer Project, and for that I apologize. I have had just a lot of other things going on, and some other kind of shiny objects that grab my attention, and I am trying to get back on track with this. And one of the things that has been consuming some of my time recently is I've had to travel back and forth across the country for some family stuff, and that during that time on the airplane, I have been spending some time building up simulations for some of the circuits in the playground, mainly for demonstration purposes for inside these videos about those particular subsystems. So this one here that I kind of just finished up this evening is about the interrupt controller, and you can see there's kind of a lot of stuff in the interrupt controller, and I'm not going to go into great detail about it here. I'm going to do a whole episode on it, but I did kind of want to show it off a little bit because it's kind of nifty, I think. So that's what this little teaser is all about. So for folks not familiar with the 6809, there is a single IRQ vector that is normally fetched by the CPU when the IRQ line is asserted. And if you have multiple peripherals on the computer that can generate an interrupt, I mean, that's totally legal to do because of the way the hardware is arranged. It's an open collector, open drain, active low interrupt. So you can have multiple peripherals on the IRQ line pulling it low. But when the IRQ line is pulled low, software would normally have to go and look at each peripheral to see if that peripheral is the one that caused the interrupt. And it actually kind of has to do that every time because it doesn't know if maybe two peripherals pulled it low. It has to go check every one. So that is that's time spent not doing useful work. Most of the time. Most of the time, it's usually only one peripheral that is interrupting you. So wouldn't it be better if the software didn't have to do that? And so that's what this little module helps with. So it's kind of like interrupt mode 2 on the Z80, which allows native Z80 peripherals to not only prioritize interrupts, but also have the CPU fetch the address of their handler directly due to with a little special handshake that they do. And that's kind of what this does. And so I wanted to walk through that. So it's got a bunch of parts, but the important pieces are something that's not shown here. It's called, I call it the A bus cell. It's the address bus selector. And it has a job, and its job is to essentially determine who gets to drive the address bus at any given time. And most of the time that's the CPU. But when the CPU wants to fetch the address of an interrupt handler, the address bus selector gives the address bus to the interrupt controller. And the interrupt controller generates the address using a couple of things. The first thing it uses is this vector base register. And what the vector base register does is hold the address of a 32-byte table that's aligned to 32 bytes. And that table can be anywhere in memory, but it holds that address, and that's the base of the table that has the list of the interrupt handlers, one for each of 16 possible IRQs. And the IRQs are prioritized, the lowest priority being IRQ 0 and the highest priority being IRQ 15. So that's the vector base register, that it holds that table. The second piece is the interrupt enable registers, and that's just basically two 8-bit registers that sort of selectively enable which of the interrupts can actually interrupt the CPU at any given time. So you might have a peripheral that just interrupts constantly all the time because that's what the hardware does, and you can just say in software, I don't want that to happen. You have to go to an explicit interrupt. So if that's on IRQ4, you don't get an interrupt from that until you enable interrupt 4 with the E4 bit here. So that's what that is. And then the other thing it does is there's a bunch of logic that essentially decodes the priority of the interrupt. And then I have this thing called the interrupt mux that essentially figures out which one is the highest priority one and puts that out on the bus, and then also generates this IVV signal, which is the interrupt vector valid. And what happens when interrupt vector valid is asserted is that tells the address bus selector that that the interrupt controller has a vector address for the CPU. And so let's just kind of walk through how it works when an interrupt happens. So the first thing we need to do is we need to program the address of the vector table into the vector base register. So I've got some signals here that control the chip select and the right strobe and things like that. So let's say that our vector table is going to be located at 9F20. So let's see this. So let's put in a 9. So in poke mode. So 9. Was that D74 3 2 1 0? That's 9, and then we chip select. Do the right strobe, so that puts 9F into the vector base register, and then we want 2 0, so 0 0 0 0, that, and no, not that one, that one. Let's get rid of that. Okay, and then we do right, and then we have to go to the next byte, and then right strobe again. So 9F20 is now in the vector address register. So we can deassert that chip select, set A0 back to 0. Okay, so now we have the vector base programmed in. So now let's do something that we're going to enable. On the playground, I have a video chip on IRQ15. So I'm going to enable IRQ15. And so now what happens when the vsync interrupt happens on the video controller is IRQ15 will be asserted. And we see that IRQ goes low. And when IRQ goes low, that causes the CPU to finish what it's doing and then stack the registers that it needs to save. And then when it's about to fetch the IRQ vector, it's going to assert a signal called BS, bus status. And so when we assert that, we see that the interrupt vector valid signal goes high because the logic that is off the page here has decoded which interrupt it is, figured out the vector offset, and is telling the address bus selector, I have a valid vector address for the CPU. So the address bus selector sees interrupt vector valid, and it disconnects the CPU from the address bus, and then it comes and tells us to enable our output. So I'm going to set NOE low, and then you see what happens is the address of the handler appears on the data bus. That's what this is, the vector fetch address. So it's 9F3E, which is, what is that, 30 bytes in from the base of the table, 31 bytes in from the base of the table. And then when so it fetches the first byte, the most significant byte, and then it fetches the next byte, and we see the address is 9F3F. And once it's fetched the vector, the CPU will then deassert the bus data signal, which causes interrupt vector valid to go low, which tells the address bus selector to turn us off and connect back to the CPU. So we go there and we go into tri-state here, high Z. And then the interrupt handler is going to do its work. And then the IRQ will become deasserted. And there we go. Now IRQ is no longer asserted on the CPU. And that's kind of it. That's a quick sort of demonstration of how the interrupt controller works, so that the interrupt handler address is just fetched directly without any intervention by software. It doesn't have to go out and look at registers to figure out what's being interrupted. It just goes off and handles it directly. So that's it. Anyway, so that's what I have for tonight, and I will. I promise to get back on track with the other episodes. The memory subsystem like I said, I was doing some simulations, and some of them were for that episode, and so I'm going to be working on finishing the the sort of the slide deck on that and getting that all put together, and recording that soon, and hopefully I'll get that posted within the next week or so. So you'll have some actual new proper content to watch. But in the meantime, please enjoy this little teaser. And with that, I bid you a good evening, and we'll see you again soon. Bye bye.